Hey everyone, welcome to your Play Posit for the week. We are going to be covering angle and segment relationships in circles. If I'm not mistaken, this is going to be our last Play Posit on circles, and then we will finish up the circles unit in class on Thursday. And then we will only have one more unit left until the end of the year. So that's crazy. Go ahead and grab your notes and have that OMHS Play Posit graded assignment open and we'll get started. I wanted to share with you guys some things I did to celebrate Pi Day. A few of you may have been at our Pi Day assembly. I think I did see some of you guys there, which was awesome. I had so much fun with all the other math teachers, and this is a screenshot of just the trivia we did towards the end, and a pie. I almost ate this entire pie by myself, by the way. Granted, it was a mini pie, so this is probably like the size of my palm, my hand, like I could hold it in my hand. So maybe the size of like two normal slices of pie, maybe two and a half. I don't know. I ate it myself over the course of 2 days. So it was delicious. And then my friend, Miss Factorman, and I, she's actually another teacher at VAVA, we did a walk. We actually walked 3.4 miles. So we did more than the 3.1. Funny story, we thought we were taking the picture in a different order. So this says 4.13, but really it was supposed to be 3.14. So I hope that you guys had a good weekend. And I wanted to go over the question from last class where I said that I wanted you guys to try this on your own, and then I would go over it in the Play Posit. So it says to find the measure of the indicated angle or arc. So we're going to label what we have. They tell us that arc LM is 84. So this is 84. And then they tell us Kn is 116. Now we know it goes this direction because 116 is less than 180. It's also just two letters. So that's how we know it doesn't go, the other way in this direction. It's a minor arc. Ooh, excuse me. All right. So then I think we should start labeling anything that we can before we even look at the answers or the questions. So if we know that arc LM is 84, then that means that the angle that it intercepts is going to be half that. Remember we learned that theorem last class? If there is an angle where the vertex is on the edge of the circle, that's an inscribed angle, and we know the arc that it covers or intercepts is going to be double that. So we know the angle is half that. So if this is 84, then this is going to be 42. The angle sort of across that arc. And we can do the same thing for the angle that's across from KN, right? That's going to be this big angle here. Just make sure that you're grabbing the angle that intercepts that arc. And that's going to be half of 116, which is that 80? Why do I feel like that's too easy? Yeah, that's not 80 because 80 plus 80 is 160. I delete that. So half of 100 is 50, and then half of 16 is 8. So this would be 58. There we go. That makes a lot more sense. All right, let's see what else can we label. Anything else? Well, you know how this segment JL goes right through the center? We know JL must be a diameter if it goes through the center of the circle. So that would make this arc 180, right? Because that's half of a circle. And similarly with this side, right? This would be 180. So all we did was cut that circle in half and get 180 on both sides. Let's keep labeling what we can. I'm going to get a different color. So here we know that when two chords touch there at the edge of that circle, they form a 90-degree angle. So this is 90 degrees, then that means Well, since this is 42, then what's left? We have 48 here to make that other piece of that 90-degree angle. We also know that this is 90 degrees because it's directly across from half of the circle, right? And half of 180 is 90. So that inscribed angle covers half of that circle, so we can use that inscribed angle theorem that we learned last class. All right, let's keep looking. I think, check this out. LM is 84, and look, it covers this angle. Angle N intercepts arc LM. So we could do half of 84 is 42. Why don't we look at some of the questions and see if we can answer them? So the measure of JKL, angle JKL. Oh, yep, that's 90. MKL, that's 42. KMN. KMN. So we don't know that one yet, but I bet we could figure it out. So K to M to N. A good idea is to see what arc it covers. And if we know the arc measure, then we can go ahead and take half of it, right? And it does. It covers K to N. So we could do half of 116 again, which we know is not 80, right? It's 58. So this angle is 58 because it covers that arc KN. All right, angle JKM. Oh, we know that one. That one's 48. KLN, we know that one. That one's 58. LNM, we know that one. That one's 42. It's kind of nice to have it all labeled, right? You could definitely do it as you go. It's just I feel like sometimes, me personally anyways, I'm more visual and it just helped me to work through that picture when I could. G is the arc MJ. MJ. So we don't currently have that labeled, but let's see if it covers anything. M to J. Sure enough, MJ covers is this arc, which follows this angle, angle K. So if that angle is 48, then we know the arc across from it, JM, is going to be double 48. So double 48 is, what is that? 48 times 2. 96. Awesome. So this arc is 96. Lastly, LKJ, arc LKJ. Ah, that's half the circle, right? So we know that's going to be 180 degrees. So I don't know about you guys, sometimes these problems can be a little confusing because they're all jammed on one circle and there's a lot going on. So I personally feel like it helps to work through the circle as much as you can and then see if you can answer the questions. It's like a big puzzle. All right, so we're going to get into angle relationships in circles. So there are a few different ways you can make angles inside of circles. You can do it. Here's an example in figure number 1. We have two secant lines intersecting, and they intersect on the interior of the circle. We have two secant lines intersecting on the edge of the circle, and two secant lines intersecting outside the circle. And these all provide different scenarios, right? Like scenario number 2, we actually know this one. This is an inscribed angle that's formed. Scenario 1 and 3, we're going to cover today. So here's our first scenario. So an interior angle, I know that you guys could probably give your own definition to that, right? Interior, meaning on the inside. So an interior angle has its vertex at the intersection of two lines inside the circle. So the vertex is inside the circle. So, of course, there's a working theorem, an interior angle theorem, and that tells us that angle 1 equals the measure of arc AC plus the measure of arc DB divided by 2. So this is just an example with these letters, but to find this interior angle, actually either one of these, so we could say angle 2 also equals this. All you do is you take the two arcs that are covered by those angles, add them together and divide by 2. You're finding that average. Because this is not an inscribed angle, and it's also not a central angle, right? Those are the two we've learned. We've learned central angle, and then we've learned an inscribed angle. So we have rules for those. This is neither of those. So let's try one. So if we want to find this, now it's got to be the arc that's across from it. So we would not use JK and ML. We want to use the arcs that are covered by the angle. So it would just be 156 plus 130 divided by 2. So let's see what that is. 286 divided by 2, 143 degrees. So we know x is 143. What would this angle be? And it would be also be 143, right? Because these are vertical angles, so they are congruent. Let's look at this one. Remember I said that you want to use the angles that are across, you want to use the arcs that are across from the angles, the ones that are intercepted. So if we're looking for y, then we're going to want to use this arc plus this arc. Excuse me, or this angle and the two angles here. But we don't know those angle measures yet, do we? Nope, we only know this one. But we can find it because what kind of angles are these? These are angles right next to each other that share a side, and they are supplementary. These are adjacent angles. So to find this angle measure here, we would just do 180 minus 102. So that's 78 degrees. So that means this is 78 and this is 78 because those are vertical angles. So now let's set it up. We know that the angle, so this should have said x over here, the angle equals, so 78 equals the two arcs added together divided by 2. So see, this one's a little bit different. We know the angle measures, and we're trying to find that missing arc measure. So now we're going to solve this like we would any algebra problem. There's a few ways to do this. I would just probably cross multiply. Whenever you have two fractions that equal to each other, you can cross multiply. So 2 times 78 equals 1 times y plus 95. And then we'll just keep solving for y. We'll subtract 95 from both sides. And this is where I do want to grab a calculator. 156 minus 95. Let's see. I am not a human calculator. 61 degrees is this arc measure. And you can always double check it. You know, you would say, okay, 61 plus 95 divided by 2. Right? The two arcs across from it divided by 2. So let's see. 61 plus 95 divided by 2. Sure enough, it is 78, which is the angle that we had. So it all works out. All right, so now we can have some angles that are formed outside the circle. And there's a few ways you can do that. I don't expect you guys to like memorize these ways. I just wanted to show you visually how it can differ. You can have two secants here forming that outside angle. Remember, a secant is a line that intersects and goes through the circle at two places. Or you can have a secant and a tangent line, or you can have two tangents with 2 points of tangency to form this exterior angle. So let's get to the theorem. That's going to be the part that we want, right? The part that we need. So in order to find any of these missing pieces, I'll just show you with example 1 here. We're going to do angle 1 equals, this time, because the angle is outside the circle, we're actually going to subtract them. So the measure of arc, we can call this x, minus the measure of arc y, divided by 2. So you take the outside arc minus the inside arc and divide by 2. I'm calling it outside and inside because, you know, this is the outermost arc and this is the innermost arc. You might say left arc minus right arc, but I don't know if I would say left and right because you could have these drawn, you know, this way, and then it would be right minus left. So I just like outer minus inner or big minus small. And once you work through these enough, you're going to get used to the theorem. So let's try one. Here we have an exterior angle. So the exterior angle equals the outside arc, 178, minus the inside arc, divided by 2. So 178 minus 76 divided by 2. 51, x is 51 degrees. And we're done. Now let's try example 2. It's the same exact theorem. It's just going to be a little bit different because you're looking now for the arc measure. So let's set it up the same. The outside angle equals the big arc minus the little arc, or the outside minus the inside, divided by 2. Now we have to solve for a this time. So again, we can make this a fraction and cross multiply. So 30 times 2 equals a minus 44. So if 60 equals a minus 44, just add 44 to both sides, and you get a equals 104 degrees. 104. And again, you could sort of check that, right? We would do 104 minus 44 divided by 2. 144 minus 44 divided by 2. And that is 30 degrees, which is exactly what that exterior angle is. All right, moving right along to segments inside circles. Segments and circles just keep on going. So we're also going to have, we just talked about angles in circles, right? And now we're going to talk about segments in circles. So we can have intersecting chords. Now this looks very similar to the theorem we've already done, right? But that's when we were talking about the angle measure. Remember, to find this angle measure here, we did this arc plus this arc divided by 2. But now we're going to be talking about these segments that the chords form. So here's our definition, or sort of our theorem. We can kind of combine these. When two chords intersect each other inside the circle, C-I-R-C-L-E, then the products of their segments are equal. And I'll show you what that means. So it's up to you, actually, if you want to write this theorem or not. I would probably just write the working theorem, which I'm about to show you. So all this means is that A times B equals C times D. Each of these pieces, A times B equals C times D. The products of their segments are the same. So each piece multiplied together is going to equal the other two pieces multiplied together. So let's try it. Find the value of x. So we'll do 4 times 6. 4 times 6 equals x times 3. And let's just solve for x. So 24 equals 3x and divide by 3. x is 8. And that makes sense too if you look at this because it's the largest segment visually and it's the largest number. Let's try the second one here. 10 times 18, so each piece, right, equals 9 times the whole other piece. Make sure you put that whole other thing in parentheses. So we'd have 180 equals, don't forget to distribute your 9. So 9x minus 27. We'll just keep solving for x here. And divide by 9. I wonder if I can do this one in my head. You guys double check with your calculator. Let's see. 9 goes into 20 twice with 2 left over. And 9 goes into 27 3 times. Is it 23? 207 divided by 9. Let's see. Yes, it's 23. Great. So x is 23, which means this piece of the segment is 23 minus 3, which is 20. And again, visually, that does make sense. It appears to be the longest piece, and we did find the largest number there. So let's keep on going. This is when we're going to have intersecting secants and tangents. So I'm going to get straight to the theorem. Here is our theorem page, if you will. So here it is. This is probably the strangest one to me. And if you guys ever take college geometry, then your professor will spend so much time proving these different theorems to you. It's very interesting and helpful. You can kind of see where things come from. I wish we had time to do all of that. For now, it kind of becomes just a working theorem for you, right? Like a working theorem sheet, if you will. Sorry, you guys, I was having some issue there with my screencast, and I hope that everything is to watch this back and make sure you're good to go. Here's our intersecting secants theorem. And I kind of think of this one as like part times the whole equals part times the whole. And I'll show you what I mean by that. So if we looked at this example, the piece would be A, that's the part. So A times the whole thing. Now we can call this whole thing E if you want. You can also call it A plus B. You see how they're the same thing labeled here in this? So B, A plus B, or we've labeled it E. However you kind of want to imagine that. Equals the part, the outside piece, times the whole thing. So we could say F, or we could say C plus D. The way that we have this diagram labeled here. But it's the part, the outside piece times the whole thing, and then the outside piece times the whole thing. So let's try one. The outside piece, 6, times the whole thing. So the whole thing here is going to be 15 equals the outside piece times the whole thing, 5 plus x. So that's maybe better. Outside piece times the whole thing. Very mathematical, isn't it? Outside piece times the whole thing. And then we can just solve this mathematically, right? Algebraically. 5 times 5 is 25. 5 times x is 5x. What is 15 times 6? Well, 10 times 6 is 60. And then 5 times 6 is 30, so that's 90. You can always use your calculator. In fact, I might do that soon here just to make sure we're going on the right track. So 90 minus 25 is 65, and then we'll divide by 5. 13. Divide both sides by 5, and you get x equals 13. Let's try it again. I'm going to get a different color. Don't forget, I know I haven't said this yet, but you guys can always pause the recording at any time to try these on your own. Right? So the outside piece times the whole thing, x plus 3. of course I did not give myself enough room. Let me write it down here. Equals the outside piece times the whole thing. The whole thing is 12, 10 plus 2. So we'll distribute the 3. 3x plus 9 equals 24. Minus 9 is 15, and divide by 3. So you see, I feel like a lot of geometry is mostly algebra, right? There was like 10% geometry, learning how to set up this intersecting secant theorem and then just solving it for the variable. So we have another theorem. It's very similar, except this time, instead of two intersecting secants, we have a secant and a tangent. So BA is a tangent, right? It's point B is the point of tangency. And then we have the secant going through the circle. So this one is the tangent piece squared equals the outside piece times the whole thing. So because we don't have like an outside piece whole thing here with the first segment, that's why we're squaring it. You could also write it like this, right? The way it's written, you could write B times D. They mean the same thing. So let's try some. We're going to do the tangent squared equals the outside piece times the whole thing. That's 4. So x squared equals 4. Remember, to get x by itself, the inverse of squaring is square rooting. So x equals plus or minus 2. Remember, when you square root something, you can have a positive answer and a negative answer. Because if you think about it, positive 2 times positive 2 is 4, and negative 2 times negative 2 is 4. But let's see which answer makes sense for the question, right? We're talking about the length of a segment or the length of a line. So you're not going to have a negative length. So we do want to grab the positive solution. Let's try another one. The tangent squared equals the outside piece times the whole thing. So we're going to have x plus 10. All right, this one's looking interesting. So x times x is x squared, and x times 10 is 10x. Look at that. Do you guys remember from algebra how we have a squared term and an x term? So we're going to need to factor this. Remember when we factored, we got it to look like that. So let's get everything on the same side. I'm going to move 144 over. So we have x squared plus 10x minus 144 equals 0. Now that we have everything on the same side, we can go ahead and factor. And how you learned how to factor or how you like to factor. I like to factor using what I call the MA chart. And if you had me last year, you'll likely remember this. Remember, we're looking for two numbers that multiply together to give us the first times the last. So that's negative 144x squared. To add up to give us the middle term. And that's why it's called the MA chart. Multiply to give us this and add to give us this. So step 1 is just listing the factors of negative 144. Like what times what is negative 144? And we know it's negative 1 and 144. 144, negative 144 and 1. Oh my goodness, there's going to be so many. Because 144 is so big. So we're going to have to get to some bigger numbers. Like we know 12 and 12 is 144. And you can even use your calculator to help you. Let's see, 144 divided by 14. Does that work? Nope. 144 divided by 16. Ooh, so 16 and 9, that's another pair. We're looking for the pair that adds to give us 10. So that doesn't add to give us 10, but we're on the right track. So let's see if 17 goes in. Nope. And I just like to be very methodical. Let's see, 18. Oh, 18 and 8. Ooh, 18 and 8. That is promising. So we could do a positive 18 and a negative 8. Look at that. That gives us 10, doesn't it? 18 minus 8 is 10. So we replace the middle term with those two numbers, 18x and negative 8x minus 144. Now we can factor by grouping. So group the first two and group the second two. And let's see what these first two share. What is the greatest common factor of the first two terms? And they both share an x. So we're going to take out an x, meaning we're going to divide each of these by an x and see what's left. So the first term, there's an x left. Second term, there's just 18. The second pair, what do they share? Well, we know they have 8 in common. So negative 8 divided by negative 8 is a positive 1x. Negative 144 divided by negative 8 is a positive 18. Remember, those were the factors. 8 and 18 give us 144. And look, we know we did it right because these two match. When you do that, all you have to do to write the final answer is grab these two, x minus 8 and x plus 18. So then we're going to solve each of these for x. So you get x equals 8 and x equals negative 18. Now again, similarly to this first one, we know we're not going to choose negative 18 because you can't have a negative length. So the answer is 8. Now I realize this was kind of like a blast from the past, right? This whole factoring. So maybe I'll put an extra link for factoring practice, or if you guys need help, come to office hours or reach out to me because you will see factoring here and there. Let's do this last one. So the tangent squared equals the outside piece times the whole thing, 5 plus x. So 49 equals 25 plus 5x minus 25 is 20. Is that 24? Just don't want to make a mistake. I feel like, because now look, it's not going to go in evenly. So let me just double check my math here. 7 times 7, that's 49. Yep. And then 5 times 5 is 25, so minus 25 is 24 divided by 5. Oops. All right, so we get a decimal. We get 4.8. I guess that's fine. Decimals are okay. All right, moving right along to our last topic, and that's sectors. So I feel like sectors are pretty user-friendly because they're things that you guys are used to. Like this slice of pizza is a sector of the circle. It's a section of the circle, if you will. Here's some radar. We have this the sector here. It's like a piece of that circle. Here's another one. Piece or fractions of a circle. So we can write that definition. A piece or fractions of a circle. And the formula for area of a sector is pi times r squared, and then you multiply by the angle over 360. So area of a circle, oops, area of a whole circle is pi r squared, right? I just wrote pi. When you're going to take the area of a piece of a circle, it makes sense that you just multiply by that piece, that angular piece. So whatever the angle is over the entire 360. So let's try it. The diameter is 8. What is the area of the sector bounded by the 144-degree arc? So we're going to use our formula. All right, so the area is, now the diameter is 8, so that makes the radius 4, right? Now the angle measure they're asking us is 144 degrees over the entire circle of 360. Now we just have to do this math, and definitely want to use your calculator for this. Your Desmos calculator likely. I don't think my computer calculator has pi, but we can just use 3.14 as well. So 4 squared is 16. Let's see what 144 divided by 360 is. That's 0.4. Now they're both in degrees, so that's good. If it were in other, you can also measure angles in radians, but likely that's not part of your standards this year. You should only see degrees. Radians means it's just in pi though. So it's just a different way, like centimeters and inches, pi and degrees. So now let's do 16 times 0.4 and then times pi. 20.1. Or they might have you leave it just with the pi. So 16 times 4, 16 times 0.4 is 6.4 pi. So make sure that as you're doing these, you're looking at how the answer choices are given or how they want you to give the answer and do it that way. Here's another one. Which best represents the area of the shaded sector? So see, these answer choices are leaving pi in the answer, so they're not multiplying it out. So let's do this. Area equals pi times r. It does not tell us what r is. It tells us that WP is 36. So if the whole thing is 36, then half of that would be the radius, right? So half of 36 is 18. So that's our radius squared times, now be careful here, this one, remember, we want the angle that's bounded by the shaded region. That's the sector we care about. So that's the angle we want to use. We don't really know that angle yet, but we know that half the circle is 180, and they already used up 50, so this must be 130. So be careful there. Sometimes you have to figure out that angle measure before you can use it. Now we can plug this in the calculator. So 18 squared is 324. And then 130 divided by 360. That's 0.361. Then multiply that by 324. Because we want to leave pi alone. 117 pi. Because the answers, again, were left in pi. So don't make the mistake of multiplying all of this by pi and then being like, oh, my answer is not there. They just want you to leave it with pi in the answer. There it is. Last one, this gives us 3 concentric circles. So concentric circles are circles that share the same center. You can think of like when you drop a pebble into a lake or a pond, you know, you see those ripples come out from the center where that pebble dropped, forming those concentric circles. So there's some special things about concentric circles. As they go out here, they tell you KL, LN, and NO are all congruent. KL, LN, and NO, all of these little segments. And the whole thing is 42 inches, which is the closest to the area of the shaded region. So there's probably a few ways to do this. I don't know about you guys, but I first see, like, let's find the area of half the circle and then try to subtract out the area of the inside circle. You could try to do that. So the area of the half the circle is going to be, well, let's see, if this whole thing is 42, actually, we might not even have to do that. Let's just see. So the whole thing is 42, which makes the diameter, I'm sorry, the diameter is 42. So the radius would be half of that. So that is 21. So we actually don't have to do what I first said because of this. Because they tell you all of those pieces are equal, congruent, that means we can split 21 into 3 equal pieces. Perfect. Okay, so let's find the area of half of that sector. We know how to do that. We can worry about this little piece we need to subtract out after. So I think we do still need to do that. Let's see what happens. So we're going to use our formula. Area equals pi r squared times the piece of that circle. So angle over 360. We're going to do half the circle. So we're going to pretend like this area is shaded, but then we're going to subtract it out in the end. So we have the radius is 21 of that whole half that circle, and the angle is 180. We're going to put all of that into the calculator. So 21 squared times 180 times pi divided by 360. 692.37. Now the reason I multiplied by pi this time is because look, the answer choices do not have pi in it at all. So that's the whole half of the circle. You could have also found that by just doing the area of the circle and divided by 2, right? So let's take that idea then. Let's find the area of the small inner circle. So the area of that small inner circle, remember area of a circle is just pi r squared. Just like a good old-fashioned circle, not a sector, not a piece of a circle, just the circle. So the radius of that little circle is 7, right? Remember we found each of those little pieces are 7. So what is this? 7 squared times pi. 153.86. So that's the entire little circle. But we only want to subtract out half of it, right? This little piece. So divide that by 2 and see what we need to subtract out. 76.93. So we need to take that entire area that we found and subtract out that semicircle of 76.93. And let's see what we get. 692.37 minus 76.93. 615.44. Let's see which answer is that closest to. I would say it's definitely closest to D, right? This would not round to 615, but it's definitely the closest to that area. I will say, you guys, this is probably the hardest that these kind of questions will get. So working yourself through them is going to be very helpful. This actually came from TestNav. And by now, you probably know what TestNav is, but it's basically like a practice site for the SOL. Like it's a simulation of what the actual test will look like and feel like and be like. So it's a really good site to check out. It's in your SOL resources link as well, so you can always find it there. So last but not least, do not forget about the circles formula sheet that I have for you guys. You cannot use this on tests or the SOL, not this particular theorem sheet. This is one that a student made for me a few years ago as an assignment. And I just thought it would be helpful for you guys to have all the theorems in one place as you're learning them, working with them, studying them. So that is there for you in your OMHS. I know that today was a little bit longer, and I believe we don't have anything else on our plan for today. So you don't have any other math lessons. So I will see you guys on Thursday in class for the last part of our circles unit. Bye, everybody.